So now we'll go through the processes of the first reaction in photosynthesis, which is the light reaction. Before we get into the actual flow, we want to look at some of the players. And one of the things that's going to happen in the light reaction is that the pigment chlorophyll is going to absorb some light from the sun. And when it does this, it's going to become excited. What we mean here is that an electron in the chlorophyll molecule is going to gain some energy. And when it gains some energy, it is going to come to a higher state of free energy. So this can be considered the free energy of the electron. So the photon, the packet of energy from light, is going to provide energy to this electron, which is going to put it in this excited state. Electrons can't stay in an excited state on their own without a constant input of energy. So what happens is it's going to fall back down to the ground state. And when an electron falls back down, some of that energy is usable. So for example, if this one's just falling back down, it might fluoresce and emit light energy, or it might transfer that energy to another molecule, like in an electron transport chain. And some of that energy is going to get lost as heat. We know this as the second law of thermodynamics. Every time we change energy, it's going to lose some as heat. If this was just looking at a pigment, so this is just a pigment with its energy, with its electrons, we would see the electron get excited, and then it would fall back down and create a little bit of an afterglow called a fluorescence. But the pigments in a plant cell are not in isolation. They're next to proteins that can actually accept those electrons. So what's going to happen is when the electron falls back down, instead of going back to the chlorophyll, it's going to move over to an electron transport chain, which should be familiar because that was the last step of the cellular respiration process. The chlorophyll molecules are actually stored in a complex system called a photosystem. So the photosystem is a region on the thylakoid membrane that is going to be able to absorb light. And it consists of a couple of different regions. In the center, we have a reaction center complex. This is going to contain a special pair of chlorophyll molecules. These are the ones that are going to be donating electrons to be excited, as well as a primary electron acceptor. So this first region up here is going to accept that excited electron and then eventually pass it off to another molecule. Surrounding this center, so you imagine this is a whole sphere, like a donut, is what's called a light harvesting complex. And this consists of different pigment molecules. So we have all of these green chlorophylls. We could have different pigments as well besides chlorophyll here. And those are going to absorb the actual photon of light, and they're going to pass that energy along between them until it gets to the center. So throughout this process, we're going to see two different photosystems, and they are going to, ironically, be in reverse order. The first photosystem we're going to see is actually photosystem 2. And the reason that they are not named in the order that they occur is because we discovered photosystem 1 first, and then we discovered photosystem 2 later, and we just named them that way. So this actually is going to happen first, and then the electron is going to get excited in photosystem 2. The reaction center for photosystem 2 is called P680 because it absorbs at a wavelength of 680 nanometers. So you can call this first photosystem either photosystem 2 or P680. It's up to you. Eventually, the electron is going to get excited, and then it's going to get passed all the way to our second photosystem, which is photosystem 1, which we also call P700 because it gets excited at a wavelength of 700 nanometers. So just remember that photosystem 2 comes first, and then photosystem 1 comes second in this whole process of the light reactions. So throughout the light reactions, what we're going to see is called linear electron flow. Linear just means in a straight line, And then electron flow, we're going to kind of be following the movement of the electrons. Just like in the last step of cellular respiration, oxidative phosphorylation, we followed the movement of electrons and energy. We're going to do the same thing here. There is a cyclic route, and we believe that the cyclic route actually probably developed first, and then linear electron flow developed after that as far as evolution goes. But the plants that you see in your yard, your grass, your trees, are all going to be doing linear electron flow. This is the primary pathway, and it's going to produce energy in the form of ATP and NADPH from the source of light energy. So we are over here, and it is important to note that the light reactions are happening on the thylakoid membrane. Remember back to cellular respiration, how the electron transport chain happened on the inner mitochondrial membrane? Well, again, here we are having an electron transport chain on a highly folded thylakoid membrane. So we will go step by step. Step number 1. Light energy is going to hit a pigment of photosystem 2, and it's going to pass the energy until it excites the photosystem. So here we have the light energy coming in, hits a pigment. It's going to get passed from pigment to pigment until it randomly hits the reaction center complex. So once it hits this dimer of P680, the chlorophyll here that absorb at 680 nanometers, the electron gets excited up to the primary electron acceptor. So this primary electron acceptor has now got a negative charge because it has gained an electron. It has gained an electron, so it has been reduced. This chlorophyll here lost an electron, and it's not coming back. It doesn't get its electron back. So it was oxidized. Being oxidized makes it extremely electronegative. So electronegative that it can now pull electrons off of a very electronegative molecule like oxygen. The primary electron acceptor is called P680. We need to deal with the fact that this reaction center is extremely oxidized. It's very unhappy. It lost an electron and now it needs a replacement. So it is so oxidized and so electronegative at this point that it is going to be able to pull electrons off of oxygen, which is a very hard thing to do. So it's going to be able to replace its electrons by splitting water. This is the whole reason you have to water plants. So next time you water a plant, you can tell the plant to be very thankful for its replacement electrons. P680 plus actually has to be the strongest biological oxidizing agent, meaning that it's the most electronegative molecule possible because it's pulling electrons off of one of the most electronegative molecules, which is oxygen. The hydrogens just get released into the thylakoid space. They're actually going to contribute to a proton gradient later on, which we'll see is going to be important. The oxygen is just released as a gas. This is a waste byproduct of this reaction, so the plant is just going to release oxygen at this point, and then you can use it to inhale and breathe and do cellular respiration. So now that we've replaced the electrons here, P680 is going to go back to being P680 and not P680 plus anymore. And the electron that got excited is going to fall down the electron transport chain. So we've got another electron transport chain. Again, we've got the molecules, the names of the proteins in the book if you want to learn them, but you don't have to. So we're going to see a transport here, here, here. And this electron transport chain works exactly the same way as the electron transport chain in cellular respiration. It is going to store energy in a proton gradient. So this time the hydrogens are going to be moving into the thylakoid space, which is where these ones are. Every time we move an electron, more hydrogens get moved across. Every time we move an electron, more hydrogens get moved across. This is active transport because we are using free energy that's being released to move hydrogens across the membrane. On the other side of this membrane, we're going to have that ATP synthase that's going to use these hydrogens to create ATP. So the electron transport chain here is where we're going to make ATP. This is the exact same process of chemiosmosis that we saw in cellular respiration. At this point, you can see this graphic is kind of using this axis as a free energy diagram, where this is low and this is high. When the electron was excited, it had a high free energy. As it was being transferred, the free energy actually dropped. So by the time we get to P700, the electron is being transferred here. This electron is actually a replacement electron for P700. So P700 doesn't need to split water because it's being given electrons from P680. In order to get another process going, we actually need another boost of energy. So this reaction center complex is also going to absorb light from the sun. So we're going to transfer light energy to P700, so it gets absorbed at a pigment, it gets passed along on the different pigments until it eventually reaches the chlorophyll dimer in the middle. My electron is going to get excited up to the primary electron acceptor, and now we can call this P700 plus. The P700 is missing an electron now, right? It got transferred up here, but that's okay. It's going to receive another one from the electron transport chain in a moment. And then the next step is to fall down another electron transport chain until it reaches the primary electron acceptor, which is called ferredoxin. Even though you didn't need to learn the names of the other proteins, this one is a name you do need to know, is ferredoxin, which is here FD. That is the protein that is then going to give the electron to NADP+, which will turn it into NADPH. So we can see ferredoxin here giving electrons to NAD+. This is just an enzyme, NADP+ reductase, because it's going to reduce NAD+. Here's the hydrogen plus an electron, and then this is going to create NADPH. And so this is my temporary energy storage molecule that we will then be able to use to power the next Calvin cycle. Notice that this process happens in the stroma. So the NAD+ is created in the stroma, and the ATP is also created in the stroma. So that's that liquid that surrounds the outside of the thylakoid membrane, which is really convenient because that is where the Calvin cycle is going to happen in a minute. So here you can see kind of the pathway of the linear electron flow, and highlighted in color, you can see what would be considered the cyclical electron flow. So cyclical electron flow would include only photosystem 1, so this is P700, which is going to get excited by light. We'll pass that excitation until it gets to the primary electron acceptor here. The electron gets excited, it gets passed to ferredoxin, and then instead of ferredoxin giving it to NADP+, ferredoxin actually just gives it back to the electron transport chain, which is going to eventually give it back to P700. So you can see that this is kind of an electron cycle where the electron gets excited and then passed back to its original molecule here. This is going to produce ATP, which is great. So this will produce a little bit of energy from the solar light energy here, but it does not produce NADPH and it does not release oxygen. So this by itself cannot provide a plant with the means to do photosynthesis. What we think that this is that this was an early version of photosynthesis that happened before photosystem 2 and the Calvin cycle evolved, and this would have provided the plant with a little bit of energy, and we use it now as a method of photoprotection. So if there's an excess amount of light energy coming into the plant, some of that energy can actually be powered to just do cyclical electron flow to help prevent any damage to the plant, and still produce a little bit of ATP at the time. So let's take a minute and kind of go all the way back to the beginning of the light reaction and go through and kind of highlight all of the things that you need to know and review here a little bit. The first thing that's going to happen is we're going to have light energy that's going to react with photosystem number 2, or P680. That is going to excite an electron here to the primary electron acceptor. That primary electron acceptor, P680+, is extremely electronegative, very high oxidizing agent, and so it is going to pull replacement electrons from water, resulting in oxygen that's going to get released from the plant. The excited electron is going to get passed down this electron transport chain, And as it does, it's going to build up a proton gradient of hydrogens, which will then go through ATP synthase to create ATP in the stroma. Notice the ATP synthase, just like in cellular respiration, it's next to the electron transport chain, but it's not actually a part of it. The electron is now over here in photosystem number 1. The photosystem number 1 is now low here again on energy, so we're going to have to absorb light energy again to excite that electron up to the primary electron acceptor. Primary electron acceptor is going to give that molecule to ferredoxin, which is going to give the electron to NADPH. And in the process of giving it to NADPH is going to store a little bit of energy in this molecule. And now we've got 2 energy storage molecules, NADPH and ATP, that are in the stroma, ready to move on to the Calvin cycle.